Good morning, all you positive people. In 6.2, we're going to look at growth and decay models, which is going to be somewhat of a review from Algebra 2, but it's good to see this, especially when I haven't seen it in a while. And there's going to be a little calculus involved when it comes to coming up with the exponential functions, but then the rest of it is going to be very much just algebra. Um, so the two things that I want to get out of this is use separation of variables to solve some simple differential equations. Not simple, separation. And instead of writing differential equations, I'm just going to call them DEs. Um, and then the other idea is we're going to solve one, and then we're going to come up with an exponential function that is the solution, and we're going to use that exponential function. Use exponential functions to model growth and decay in applied problems. Okay, so first thing is separation of variables. What is that? The strategy is going to be to, given a differential equation, we're going to try to rewrite it so that the equation of each variable is on one side of the equation. So we write the equation so each variable occurs on only one side of the equation. And we're going to do more of this in the next section. We're only going to use this technique once this time, but more so in 6.3. And then we integrate both sides. Yeah, and you can see I'm actually writing everything down, so you guys have time to write it down with me instead of me having you pause the video and copy down the example. So try to solve it this time. We'll see how that works. But here's an example. Let's solve the differential equation. So what that means again is find out what the original function must be given that the rate of change is equal to 2x divided by y. So this idea of separation of variables is we want to put all the y's on one side and all the x's on the other side. Just to get in the habit, it's going to be helpful to, instead of writing y prime, we're going to rewrite that as dy dx because that is another way of writing the derivative. Because now the separation of variables part is going to be a little bit easier. There's a y on both sides. I'm going to multiply both sides by y to get rid of the first y. And then I'm also going to multiply both sides by dx. I'll do that in the second step so that we don't go too far. So y times dy dx equals 2x. And then I multiply both sides by dx to get all the x's together. So now I have y dy equals 2x dx. So separation of variables, I got all my y's on one side, all my x's on the other side. And then the next thing is to integrate. So we're going to integrate both sides. Right. Think of it as like you can add both sides. You can add two to both sides. You can double both sides. You can divide both sides by 7. You can integrate both sides. The equality will hold. So the antiderivative of y is going to be 1/2 y to the second, and the antiderivative of 2x is going to be 2x squared over 2. The 2's cancel out, and don't forget the plus c. And this is the solution. So I'm going to write 1/2 y squared equals x squared plus c. The book writes it a little bit differently. They call this c1. And what they do is they multiply both sides by 2. So it becomes the 2 and the 1/2 cancel out, and you just get y squared equals 2x squared plus 2 times c1, which they say, let c be 2 times c1, because if you double a constant, it's still a constant. So doubling a constant doesn't really matter. And I think the back of the book either leaves it like that, or I think they put the x's and y together. But the idea is this is fine for what we're doing. This is our solution. And this is the book just simplifying it a little bit. Either way, that's a general solution to the differential equation. Okay. All right, so that's the idea. Now let's look at growth and decay models. And you guys probably have seen some of these in science before. Okay, so in many examples in differential equations, we're going to see the rate of change is proportional to the value of y. I'm going to write R of CH, the rate of change of y is proportional. Not proportional to the value of y. So let's let y be a function of time. Then what that means is the derivative, which I'm going to call dy dx, the rate of change, is proportional to the value of y. So it's related to y by some proportion, call that k. So this is me saying the rate of change of y is, so that equals, the rate of change of y is proportional to, so this is a proportionality, the value of y, proportional to the value of y. Okay, so algebraically, dy dx equals ky is how we can represent that the rate of change of y is proportional to the value of y. Okay, so I'm going to tell you the solution to this differential equation, and then we're going to actually do it together. But let's write this here. So the theorem is just going to be the solution to this, but I'm going to write the theorem as the book states it. If y is a differentiable function, so we can take the derivative of y, as long as the derivative exists. So it's a differentiable function of t. Such that y is going to be positive, and the rate of change of y is proportional to y, which is what we said y prime is ky. Then the solution is y is just equal to some constant times e to the kt. C is going to be the initial value. K is what we call the proportionality constant. And if k is greater than 0, we're going to see exponential growth. If k is negative, in other words less than 0, that's when we have exponential decay. Okay. So C is the initial value, and K is what we call the proportionality constant. E is just the natural base E, which is like 2.718. It's kind of like pi. And T is time and whatever the problem calls for, years, days, minutes, etc. So let's solve the differential equation to see how we got y equals C times e to the kt. So I'm going to show that to you or prove it to you. So here's y. So given that y is a differentiable function and it's positive, and the derivative is proportional to y itself, or the rate of change is proportional to the value of y, Then let's solve this by using differential separation of variables. So I'm going to rewrite y prime as dy dx. That's equal to k times y. Now if I multiply both sides by dx, to get the dx, get that here. Hold on, k times y. Alright, so if I multiply both sides by dx, the colors are being a little silly here. The dx cancels out, and I get the dx over here on the other side. I'm also going to divide both sides by y to get the y's out of here. So I know I did two steps in once, and I hope that didn't lose anybody. What I have now is 1 over y times dy equals k times dx. And then from this step here, we're going to integrate both sides. The antiderivative of 1 over y is the natural log of the absolute value of y. And the antiderivative of x with respect to, oh, we got to do t, not, it doesn't matter if you call it x or t, I just want to call it t because we're talking about time here. It's going to be kt plus some constant. And because y is positive, there's no sense of taking the absolute value of it. If it's positive, the absolute value of it is the same thing as y itself. Since y is positive. And now we got to go back to exponential functions a little bit here, or excuse me, the natural log function. And if I want to solve this for y, because the goal is to solve the differential equation, I want to get y by itself. What I can do here is what's called exponentiating both sides. I'm going to make both sides my exponent, and I'm going to make my base e. So if I take e to the natural log of y, that's going to be equivalent to taking e to the kt plus c because their exponents are the same. The purpose of that is that these are inverse functions. So now I can get the natural log out of there, and that leaves me with just y. Now on the other side, e to the kt plus e to the c is what y is equal to, and I'm going to do a little bit of simplifying. E to the kt plus e to the c is equivalent to e to the kt times e to the c. What I'm using is the idea that x times a times x to the a times x to the b is x to the a plus b. And so I'm just kind of going backwards with that. So I kind of have like, so to speak, I have x to the kt plus c. That's the same thing as x to the kt times x to the c. So just using that old exponent property. I know I just turned an e into an x and really didn't do much, but that's what's going on here. And the reason why, I'm going to put a c1 here for a second, because there's going to be a different c. This piece right here, there it is just a constant. E is a constant, C1 is a constant. So if I let C, my constant, be e to the C1, that's fine because e to the C1 is just some constant. So then we're going to rewrite this as e to the kt times some constant, and the book just puts the C first. So this is the solution to that differential equation. And this is what we're going to use in the next few problems for growth and decay. I'm going to do one or two, probably two in this video, and then I'm going to have, we'll do a few more in class together and then some practice problems. So, let's do that. So, anytime I know that the rate of change is proportional to the value of y, I can use this equation for y. So here's example 2. Oops. I'm actually going to write in blue. The rate of change of y is proportional to the value of y. And we're also given that when t equals 0, the value of y is 2. And when t equals 2, y equals 4. And the question is, what is the value of y when t equals 3. Okay, so we're told that the rate of change of y is proportional to y. That first sentence tells me that y is equal to c times e to the kt, because if the rate of change is proportional to y, then y must be of the form c times e to the kt. Okay, so when t is 0, y is 2. So using this piece of information right here, I'm going to replace y with 2 and t with 0. And the reason of this is I'm going to try to solve for c and k, because I want to be able to plug 3 into this equation, but there's a k and a c that I don't know what they are, and this is going to allow me to find that. When t is 0, this is going to become c times e to 0, which is really just c times 1, which is just c. So c is 2 in this case. So the equation y equals c times e to the kt is really 2 times e to the kt. And now I'm going to plug in t equals 2 instead y equal to 4. So 4 is equal to 2 times e to the k times 2. So we just have to solve for k now. Divide both sides by 2. So I'm going to get 2 equals e. Instead of writing k2, I'm going to write 2k. And now we have to solve for this exponent. And what I'm going to do is take the natural log of both sides. And that will undo the exponentiating. So just kind of like up here, exponentiating undoes the natural log. The natural log undoes exponentiating. So the natural log of both sides, the e and the natural log will undo each other. So whatever the natural log of 2 is, that's equal to 2 times k. So if I want to solve for k, just divide both sides by 2. And so you're just going to put the natural log of 2 divided by k in the calculator. And that gives you about 0.3466. Now we found c and we found k, so now we can finally go in and find out what's the value of y when t equals 3. So we have our equation, 2 times e to the kt, 2 times e to the, and I know I know what k is now. So if y equals 2 times e to that value, when t is 3, we can just plug 3 in and be done. E to the 0.3466 times 3. And when you put that in the calculator, it spits out approximately 5.657. And so I'm going to do another example with exponential decay, and then that'll be it for this video. So let's look at example 3. Radioactive decay. Supposing 10 grams of plutonium isotope, which is I guess referred to as 239 Pu, was released in the Chernobyl nuclear accident. I wonder if any of you guys, I heard there's a good show, Chernobyl, on like HBO or something. I haven't watched it, but it's pretty wild from right here. Now the question is, how long will it take for 10 grams to decay to 1 gram? So 10 grams are released, and over time it'll decay. How much time, how many years is it going to take for 10 grams to go into 1 gram? And there's some extra information we need here. 3 things. The rate of change is proportional to the amount amount present. So we'll call that y. Radioactive decay is measured in half-life. And what does that mean? That means that's how many years for half the atoms to decay. So I think you guys may have seen half-life in science. And for plutonium, I'll tell you what the half-life is. So for plutonium, the half-life is 24,100 years. Wow. Okay. So the idea here is I know the rate of change is proportional to the amount present. So I can write the equation y equals c times e to the kt, where c is my initial amount, k is my constant, or my proportionality constant, and t is the amount of years. So y is going to be the amount of plutonium in grams, by the way. I'll write that here on the side. So we're told that the initial amount C, C is the initial amount, and the initial amount is, in this case, 10 grams to start. So y equals 10 times e to the k. If the half-life is 24,100, in 24,100 years, there's going to be half the amount left. So when t equals 24,100, the amount is going to be half of what we started with. So half of 10 is 5 grams. So I'm going to use that in the equation here. I'm going to replace y with 5. So y equals 10, which is 5 equals 10 times e to the kt. And t in this case is 24,100 times t. So let's divide both sides by 10. 5 over 10 is the same thing as 1/2, by the way. And then take the natural log of both sides to get the e out of there, and then get the exponent out of get the t out of the exponent. So the natural log of 1/2, whatever that is, the e's the natural log cancel out, is equal to 24,100 t. So just divide both sides by 24,100. And in the calculator, it should tell us that t is 24,000 is t, and we're searching for k. Sorry about that. This is k, not t. So we're not searching for t, we're searching for k. We're given t is 24,000. So that's just k. And this is about negative 0.401234, 28761. So we have c and we have k. Now the final question is, at what point is the, or how many is it going to take for it to be only 1 gram, not 5 grams. So I'm going to use that information here. So my equation here for the amount of plutonium is going to be 10 times e to the k, which I know is negative 0.12340, 28761 t. And the question is when this is going to happen when y equals 1 gram in the problem computer. So I'm going to replace the y with 1 and solve. Okay. So divide both sides by 10 like we did before. So 1/10 equals e to the negative 0.12340 to 87176.1. And then to get the e out of there, take the natural log of both sides again. So the natural log of 1/10, the natural log of e cancel out is equal to that negative 0.12340 to 87161 times t. The t already disappeared. And then divide both sides by that long decimal. And it comes out to be about 80,059 years. So in about 80,000 years, that 10 grams of plutonium will turn into 1 gram of plutonium. Anyways, that's it for the video, and we'll do a couple more examples next class.